In this lecture, we're going to cover 2.5 transformations of functions. First, let's start out with graphs of common functions. So below are a list of common functions that are frequently encountered in algebra. You're probably familiar with some, if not all of them. The first function we're going to look at is the constant, f of x is equal to c, or y is equal to c. And we actually encountered this in the previous lecture when we were looking at the graph of horizontal lines. So f of x equaling some constant c is just a horizontal line that's going to go through y equals c. So it would look something like this. The domain of the function is all real numbers, negative infinity to positive infinity. And the range of this function is just c because the value of the function can only be c. And the function is constant on the interval negative infinity to positive infinity. Next, we'll look at the identity function. So these functions that are listed here, what I did was I made a graph of each, and then I listed the important characteristics of each graph. So we'll go through these one by one. So the identity function is the function y equals x, or f of x is equal to x. So whatever y is, x is equal to the same value. So we're going to end up with this linear function, or this line that goes through the origin. The domain is all real numbers. The range is also all real numbers. And the function is always increasing. So it's increasing over negative infinity to positive infinity. The absolute value function, f of x equals the absolute value of x. It looks like a V. So this one I usually remember, I tell my students, think it looks like a V, the letter V, and it has a point at the origin. The domain of the function is all real numbers, negative infinity to positive infinity. So x could be anything, any real number. We could take the absolute value of whatever number we want. Remember, it just measures the distance that x is from 0 on a number line. The range of this function, though, is 0 to infinity. Because remember, distance can't be negative. So the absolute value always has to be 0 or greater. So that's why this graph is staying above the x-axis. So y has to be greater than or equal to 0. We see the functions decreasing on the interval negative infinity to 0, and then the functions increasing from 0 to infinity. And we're going to graph these functions also. So in a little bit, we'll go on the calculator and I'll show you how to graph absolute value. So things you might not have known where to find on the calculator. So we'll go through it. Let's just talk about, what the general graph looks like and its properties or characteristics. So f of x, or y equals x squared, that's our quadratic function, our standard quadratic function. We also call it the squaring function. The domain is all real numbers, right? So x can be anything from negative infinity to positive infinity. But since whatever x is, we're squaring it, and that's going to give us y. Y always has to be 0 or greater. So that's why this graph lives on and above the x-axis. So the range of this function is 0 to infinity. And the function is decreasing from negative infinity to 0, and it's increasing on the interval from 0 to infinity. We have what's called the square root function, f of x, or y equals the square root of x. So we call this the square root function. That's another common one. And it looks like this. So it has a point at the origin and it's increasing, and it lives in the first quadrant. So the domain of this function is 0 to infinity. And it makes sense because we're taking the square root of x. We can't take the square root of a negative number. So the domain is 0 to infinity. Therefore, the range of this function is also 0 to infinity, and the function is always increasing, and it increases on the interval 0 to infinity. Another common function, and the last one that we'll look at, is our cubic function, x to the third. So x to the third, it almost looks like a chair, right? It's like you can imagine sitting in a chair. The domain is all real numbers, negative infinity to positive infinity, because we could take whatever number we want, raise it to the third power. It's not going to give us a problem with output. The range is also going to be all real numbers, and the function is increasing, right? It's always increasing from negative infinity to positive infinity. So those are the characteristics of our cubic function. So now that we reviewed these, common functions that we typically see in algebra, pre-calculus, what we want to do now is let's talk about what would happen if we transform them. So we're going to talk about transformations. And what I mean by that is, what if we want to move that graph? So for example, what if we want to shift the graph vertically, upwards or downwards? Or what if we want to shift a graph horizontally? What if we want to stretch a graph or compress a graph vertically or horizontally? We might need to reflect it over the x-axis. So there's all different transformations that can take place on a function. First, we're going to start with vertical shifts. So let f be a function. We'll call the function f of x, and c is a positive real number. If we take the graph of f of x and add c to it, some constant, the graph is going to be shifted c units vertically upwards. Alternatively, if we were to take y equals f of x, take our function and subtract c, so if we were to subtract some constant from our function, it's going to shift the graph downward by c units. So it's going to be a vertical shift downward. And I'll show you this graphically. But let's do an example first. So let's look at example 1. Let's say we have the graph of y equals x squared. That's my squaring function, right? That's my quadratic, my standard quadratic. And quick sketch, it looks like this, right? That's what x squared looks like. We want to shift it 4 units upward. So if we add c to the function, that's going to be a vertical shift upward. And remember, if we subtract c from the function, it's going to vertically shift it downward by c units. So the equation of the function that's going to shift x squared 4 units upward is going to be f of x equals x squared plus 4. So if we add 4, it's going to shift the function upward by 4 units, because essentially we're adding 4 to all the y values. So it's going to be a vertical shift upward. Let's look at this in the calculator. So let's graph x squared and x squared plus 4. And I want you to see how it's going to shift 4 units upward. So let's graph x squared. And then let's graph x squared and then plus 4. So here's x squared. And now x squared plus 4 is the graph above it that's shifted up 4 units, right? So it's the same graph, except it's shifted upwards by 4 units. So let's look at the next one. Write the equation of the function that has the given characteristic. So the graph of y equals square root of x, so that's my square root function, but we're going to shift it 2 units downwards. So the equation is going to be f of x is equal to the square root of x, but we want to move it downwards, right? Vertically downwards, so we're going to subtract 2. So remember what square root of x looks like. It's that function that starts at the origin and increases in the first quadrant, right? It's this guy. So let's graph square root of x and then square root of x minus 2, just so we could see that it's going to be shifted down by 2 units. So pull up your square root symbol. So square root of x. And then now let's type in the square root of x. Make sure you get out from underneath the square root and then minus 2. So when we graph it, there's my square root function. And then right below it, right, shifted down 2 units is the square root of x minus 2. The next one, we want to shift the graph of y equals absolute value of x 6 units upwards. So we're going to take f of x, which is the absolute value of x, and we want to move it upward 6 units. So we're going to add 6. And remember, the absolute value function is that v. It looks like a v, and it has a point, right, on the origin. So we're going to shift it up 6 units. So let me show you guys how to find the absolute value in the calculator. So we need to pull up the absolute value. So we're going to press math. It's in the math menu and then number. So arrow to the right over to number, and you'll see ABS for absolute value. It's the first choice. So hit enter. And you see how it pulls up the absolute value symbol for us. And now we could type in X. And then right underneath that, I'm going to type in again, absolute value of X, then arrow out of it because we want to add 6 to it. So plus 6. So there's the absolute value of X. And then 6 units above it, you see how the graph was shifted up 6 units. And we'll do one more vertical shift. So the graph of x to the third, so my cubing function, and we want to shift it 3 units downward. So f of x is going to be equal to x to the third, but since we're moving it downwards, we need to subtract 3. And remember, that's that chair function, right? So we'll graph this one also. So let's type in x to the third. So x, and then use your exponent symbol to the third. And then now we're going to type in x to the third again. But now we're shifting it 3 units downward, so minus 3. If we graph it, there's x to the third. And then there's x to the third minus 3, right? It's the graph shifted downwards by 3 units. So that's how we work with vertical shifts. Now a horizontal shift, we're going to be shifting the graph left or right. So now we're not going to be adding or subtracting c to the y values, right? Or to the function itself. We're going to be adding or subtracting c from the x values, because if we want to move horizontally, that's going to change the x values, right? We either have to add or subtract to x. So notice now we have an inside change. So instead of f of x, then plus c, here we have f of x plus c. So you see how the change is inside. We're adding c to x. So this is going to be the graph of f of x shifted to the left c unit. And it's the opposite of what you might want to think, because you see plus c. So you're naturally inclined to shift to the right c unit, but it's actually the opposite. And you'll see when we graph it. So f of x plus c is going to be a horizontal shift to the left by c units. And then the graph of f of x minus c is going to be the graph of f of x shifted to the right c units. Again, the opposite of what you might imagine. So you'll see, let's practice. So the graph of y equals absolute value of x, let's shift it 5 units to the left. So f of x is going to be equal to the absolute value of x, but since we're shifting horizontally, it's going to be an inside change. We're either going to add or subtract from x. And since we're going to the left, right, to the left, we're going to add c. So in this case, we're going to add 5. So it's going to be the absolute value of x plus 5. And let's graph this. So again, math over to number, that's how we're going to pull up absolute value. So let's plot the absolute value of x. And then now let's plot the absolute value of x plus 5. So here's the absolute value of x. And then we see the absolute value of x plus 5, right? It's the graph of f of x shifted to the left by 5. The next one, we want to take our square root function and shift it 2 units to the right. So f of x is going to be equal to the square root of x. And now, since we're moving horizontally, it's an inside change, right? We have to either add or subtract from x. And we want to go 2 units to the right. So we're going to subtract 2, right? Because if we want to go to the right c units, we subtract c. And we'll graph one more. We're not going to graph all of these just because of time, but I feel like we've graphed a bunch so far. So you should have, be getting the hang of it. So let's graph one more. We'll finish the other ones, but let's just graph this one. So let's graph the square root of x. And now we're going to graph the square root of x minus 2, since we're going to the right 2 units. So there's square root of x, and there's the square root of x minus 2. So let's look at the next one. Let's shift our square root function 3 units to the left. So my equation is going to be f of x is equal to the square root of x and then plus 3, because we want to shift it 3 units to the left. So it's a horizontal shift. And then the last one says, take our squaring function, right, or our standard quadratic, and shift it 4 units to the right. So f of x is going to be equal to x. Now we have to add or subtract from x, right, if we're going to shift it horizontally. So we want to go to the right 4 units, so we're going to subtract 4, and don't forget to square it, right? So that's how we make a horizontal change or shift to our squaring function. You have to add or subtract c from x and then square it. So we would have x minus 4 squared. And those last two you can graph on your own and, make sure that they check out. It's also possible to reflect the graph over the x-axis or the y-axis. So if we were to take a graph f of x and reflect it about the x-axis or over the x-axis, what's going to happen is all of the y values are going to get negated, right? So imagine if I had the point, let's say this is the point 1, 3. If I were to take this point and reflect it over the x-axis, The X value is still the same, right? It's still 1, but now the Y value becomes negated. It becomes -3. So whenever we reflect about the X axis, we're really negating the Y value, or f of X, right? So Y is going to be equal to -f of X. And if we want to reflect about the y-axis, so let's take this point 1, 3 and reflect it over the y-axis. Now the y value stays the same, but the x value becomes negative or negated. So there's going to be an inside change to x. X is going to be negated. So the graph of f of -x is the graph of f of x reflected about the y-axis. So let's look at example 3. Write the equation of the function that has the given characteristics. So the graph of y equals absolute value of x, and we want to reflect it over the x-axis. So remember, if we're going to reflect over the x-axis, we're negating the y values. We're negating the function. So my function is going to be equal to negative square root of x. Because we're reflecting over the x-axis. So let's just graph this so we could see. So here's the absolute value of x, and now I want to negate. So hit your negative key, right? And then pull up the absolute value of x. So there's the absolute value of x. And then look, it was reflected over the x-axis. You see how it was flipped upside down over the x-axis because all the y values now are being negated. Now let's take the graph of x to the third and reflect it over the y-axis. So when we reflect about the y-axis now, we're making x negative. We're negating the x values. So f of x would be equal to negative x to the third, because I'm negating x now. And negative x to the third is negative x times negative x times negative x, which is negative x to the third. And we'll graph this one also. So first let's graph x to the third, and then negative x to the third. Now you see this is a reflection over the y-axis, right? Imagine taking x to the third and reflecting it over the y-axis. These two graphs would match up. So let's do one more example involving reflection. So look at example 4. Suppose the point 2, 4 is on the graph of y equals f of x. Find a point on the graph of the reflection of the graph of y equals f of x across the x-axis. So I don't have an equation, I don't have a picture of f of x, but I do know it contains the point 2, 4. So the point 2, 4 is on this graph. And we're going to take the graph and reflect it across the x-axis. And remember, when we go across the x-axis, the y values get negated. So this 0.24 is going to become the 0.2 -4 because we're reflecting it across the x-axis. So the x value stays the same, the y value gets negated. So the point -2, 4 will be on that graph. We can also vertically stretch and compress or shrink a graph. Compressing and shrinking is the same thing. I'll just put in parentheses compressing, because a lot of times I use that word, compressing, instead of shrinking. So let f be a function and c a positive real number. If c is greater than 1, the graph of y equals c times f of x is the graph of f of x vertically stretched by a factor of c. So it's like multiplying all the y values by c, right? Because f of x is the same thing as y. So it's like we're taking all the y values and we're multiplying them by c. So they're all going to be multiplied by a factor of c, and the graph is going to look vertically stretched. If c is between 0 and 1, and we multiply it by the function, so c times f of x, it's going to be the graph of f of x, but now vertically compressed or shrunk by a factor of c. And I'll show you what happens visually when we look at this. So look, example 5. What just happened there? Write the equation of the function that has the given characteristics. So if we took our standard quadratic, our square function, y equals x squared, and vertically stretched it by a factor of 7, that means that we're going to multiply the function, which is x squared, by 7. We're going to multiply it by a factor of 7. So the result's going to be 7x squared. So I want you to see what that looks like. So let's graph x squared and 7x squared. So here's x squared, and then here's 7x squared. So there's x squared. And then you'll see 7x squared, right? Looks way thinner and taller. So imagine standing on the top of this graph and taking x squared and pulling it upwards, stretching it upwards vertically. That's what's happening to this graph by a factor of 7. So all the y values are being multiplied by 7. And let's do an example of a vertical compression. So suppose we have our cubic function, y equals x to the third, and now we want to compress it by a factor of 0.5 or a half. So a half is between 0 and 1. So we know we're going to be vertically shrinking the graph. So the formula or the equation is going to be 1/2 times x to the third. And let's graph. So we have x to the third, and we'll also graph 0.5 or 1/2 x to the third. So there's x to the third. And now you see how 1/2 x to the third looks a little bit wider and flatter. So imagine shrinking it down. So if you were to be able to stand at the top of this graph and push the top of it down, it's going to get flatter and wider. That's what it's going to look like. And this is by a factor of a half. So all the y values were multiplied by a factor of 0.5. And example 6 says, suppose the 0.37 is on the graph of y equals f of x. Find a point on the graph of y equals 3 times f of x. So this graph is being stretched by a factor of 3. So what's happening is all the y values, because remember, f of x is the same thing as y, all the y values are being multiplied by 3. So if the 0.37 is on f of x, and if I multiply f of x by 3, then the new point is going to be 3, 7 times 3, right? Because the y values are being multiplied by 3. So that's going to be the point 3, 21, because 7 times 3. So that would be on the graph of 3 times f of x, that point. We can also horizontally stretch and compress or shrink a graph. But horizontally, right, that's going to affect the x values. So if we multiply x by a factor of c and c is greater than 1, that's going to horizontally shrink the graph by dividing each of its x coordinates by c. And if c is between 0 and 1, and we multiply c by x, that's going to be the graph of f of x horizontally stretched by dividing each of its coordinates by c. So let's look at example 7. Write the equation of the function that has the given characteristics. So the graph of y equals absolute value of x horizontally compressed by a factor of 2. So since it's a horizontal compression by a factor of 2, that's going to affect the x value. So the x values are going to be multiplied by 2, not the y value. So my function is going to be equal to the absolute value of 2 times x. So the graph is going to be horizontally shrunk or compressed by a factor of 2. So let's look at the graph of these. So let's first graph the absolute value of x. And then let's graph the absolute value of 2x. So there's absolute value of x. And you see that's the absolute value of 2x. You see, imagine opening your arms wide and taking that graph and shrinking it, smushing it together, right? If we were to press inwards on it, it's going to compress it horizontally. So we're shrinking the graph horizontally. And we'll do one more. The graph of y equals square root of x horizontally stretched by a factor of 1/3. So the resulting graph, f of x, is going to be the square root. Now we have to multiply x by a factor of 1/3. So the square root of 1/3 x. So we'll graph this one. So square root of x versus square root of 1/3 times x. So there's square root of x. And then you see, and you know what we could do? We could make the window, let's go to x equals 20. Just so we could see a little bit more to the right. So there's square root of x, and there's square root of 1/3 x. So you see, it's like taking the square root of x, but horizontally stretching it. So now that we talked about all the different possible transformations, let's put it all together. So in one final example, example 8, we could mix the different transformations together. You don't always just have to make a vertical change by itself or a horizontal change. We could make a horizontal change or transformation and a reflection, right? So let's just practice 3 different cases. So the first one says, find the function that is finally graphed after the following transformations are applied to the square root function, so to y equals square root of x. The graph is shifted up 2 units and then shifted left 6 units. So first, let's shift the graph up 2 units. So we're going to take the square root of x and then add 2 to it. So that's going to shift it up 2 units. Now we want to shift it to the left 6 units. So that's going to be an inside change, right? A horizontal shift. So we have to add or subtract from x. So f of x, and you know what? Let's just say first, because we'll call it f of x. So first, we're going to take the square root of x plus 2. And then we're going to take the square root. Now, if we want to shift it to the left 6 units, we're going to add 6 to x. And we still have the plus 2 on the outside. So f of x is going to be equal to the square root of x plus 6 plus 2. And you could check this by graphing it. So you'll see that the square root of x, right, our square root function is going to shift up 2 units and the left 6 and to the left 6 units. Let's look at the next one. Find the function that's graphed after the following transformations are applied to the absolute value of x. The graph is going to shift down 4 units, then shift to the shift to the left 7 units, and then finally vertically stretched by a factor of 3. So let's start first by shifting the graph down 4 units. So we're going to have square root of x, or I'm sorry, absolute value of x, and then minus 4, right? Because that's going to shift the graph down by 4 units. Then we need to shift the graph left 7 units. So then we have to make the inside change, right? So we're going to go left 7 units. So we have to add 7 to x. So we're going to have the absolute value of x plus 7 minus 4. And then finally, we're going to vertically stretch the graph by a factor of 3. So finally, we're going to stretch by a factor of 3. So 3 times the absolute value of x plus 7, and then minus 4. So f of x is equal to 3 times the absolute value of x plus 7 minus 4. And we could graph this. So we're starting with the absolute value of x. And then we're going to end up with 3 times the absolute value of x plus 7, and then minus 4. Let me go back to Zoom 6, the 10 by 10 window. So there's the absolute value of x. And then you'll see there's the graph shifted, the absolute value of x shifted to the left 7 units and down 4 units, and then stretched by a factor of 3. And we'll do one more, that last question. So it says, find the function that is finally graphed after the following transformations are applied to the graph of y equals x squared. So the graph is shifted right 3 units, vertically down 2 units, and then finally reflected across the x-axis. So first, the graph is shifted to the right 3 units. So we're gonna have x minus 3 squared. So that's gonna shift the graph to the right 3 units. Then we want to shift vertically down 2 units, so subtract 2 from the function. And then finally, we want to reflect the function across the x-axis. So that means we need to negate the function, right? Negate f of x because we want to flip it over the x-axis. So we're going to negate x minus 3 squared minus 2. So f of x is equal to negative x minus 3 squared minus 2. So we'll graph this last one. So let's start with x squared. And then we have negative x minus 3 squared minus 2. So you see how the graph was shifted to the right 3. It was shifted vertically down 2 units, but then we reflected the graph over the x-axis, right? So all the points were reflected over the x-axis. So if we graph, it might be easier to see. So look at if we graph before we did the reflection, right? So if we did x minus 3 squared and then minus 2 before we reflected. So let's graph that also. So you see that graph right there. So you see how there's that symmetry across the x-axis, right? If we were to flip it over the x-axis, they'll match up, right? So I kind of just did one step before the reflection over the x-axis. So that wraps up section 2.5. And in the next lecture, we will cover 2.6, which is finding a function's domain.